In Calc 2, you're going to spend a lot of time learning what are called techniques of integration. That is, different tricks you can use to find the antiderivative of a function. How many tricks do you think we're going to learn in this class? Well, we learned a couple, really, but I mean, as far as real tricks, you're going to learn one. And it's going to be in this section called U-Substitutions. Now, a lot of you, when you get an exam and you have a problem like this, might just look at it and go, hey, I got this. That's going to be 1/5 of 2x plus 3 raised to the 5th power plus a constant. Hey, nailed it, right? But we should be able to check this. So let's check this and see if it's right. How would I check it? How do you check that you got the right antiderivative? Differentiate. So let's find the derivative. So let's check it. So I want to find d by dx, that is the derivative of 1/5 of 2x plus 3 raised to the 5th plus a constant. All right, so the constant stuff, that's pretty easy, right? The derivative of that is 0. But let's differentiate this. Well, to differentiate that, what rule do I have to apply to differentiate this term right here? Chain rule. So the 5 comes down in front. 5 times 1/5, those cancel, right? I get a 1. So looking good there. And then what happens up here? Raised to the 4th power. Am I done? Did I get it right? No. What else do I got to do? That's the derivative of the outside times derivative of the inside. So I end up, and by the way, this 2 doesn't distribute itself. It's just going to be out in front. 2 times 2x plus 3 to the 4th power. That's not equal to my integrand of 2x plus 3 to the 4th power. I'm off by that little bit. But it doesn't feel like I'm off that much that I need to just throw out the whole approach. So the trick that we're going to need is we're going to need to figure out how to adjust for these little annoying constants. And we're going to do that with a U-substitution. Now the U-substitution is going to take a little practice, etc. We're going to go back and redo this one, so I'm just going to move on to a new sheet of paper here. But in this first example, they're going to suggest a U-substitution. And so let's see the mechanics of making that U-substitution. So I've got the integral of x squared, x cubed plus 18 dx. Now, if your first inclination is to say, all right, well, I know that at some point I'm going to appreciate having that written with exponents as opposed to a radical, that's fine. That's not bad. It's a good place to start. But let's keep in mind that the problem itself is telling you, you know what, let's let u equal x cubed plus 18. So I can substitute that in directly and I'd end up with a u to the 1/2 power. The problem is that would give me some mixed notation. I'd have x's and u's in the same integrand. You can't have that. You need to have just one variable. This is not a multivariable calculus class. So let's play around with this a little bit. In fact, let me do this. Let me differentiate this with respect to x and get du equals what? What will be the derivative there? Need some help. 3x squared. And now this is a cool thing about this notation that we got from Leibniz. We understand both of these things independently. So I can multiply both sides of this by dx and get a du term. Du equals 3x squared dx. Well, that's looking interesting. Let me rearrange my function here a little bit. And I'm going to write it as x cubed plus 18 to the 1/2 power times x squared dx. If you notice, there's a little similarity between this and this, right? Those are actually pretty similar. The only difference is here I've got a 3 and here I don't. So what I like to do is I like to solve for that missing piece, or we solve for what I actually have here. Now, there's a couple ways you can think of it. You can think of dividing by 3. I prefer to multiply by the reciprocal, so that's going to be 1/3 du equals x squared dx. And that's perfect. Now I've got a nice even trade. I can trade this for 1/3 du, and with my U substitution, I've got this equals this. So I can rewrite this in terms of u, and then I'll be able to integrate this pretty easily, I think. So let's take a look. That's going to be u to the 1/2 power times 1/3 du. Well, that's nice. Notice that I've got everything in terms of u. It's all defined in one variable. Let's bring that 1/3 out in front so I can concentrate on integrating u to the 1/2 du. So it's going to be 1/3. What's the integral of u to the 1/2 going to give me? What do we got to do? Louis? What would that be? U to the what power? 3/2 divided by 3/2. Yeah, so invert and multiply. So that's going to be 2 over 3 times 3 would be 9, u to the 3/2 plus c. Now here's a little dangerous spot for you in doing these problems. I mean, right here you feel like, whoa, hey, nailed it, yeah. But we're not done. There's one last little problem, and that one last little problem is that originally this started out as a problem in x. I don't want an answer in u for a problem that started out in x. So you got to go back and replace that u with what it was defined as in the first place. And that was x cubed plus 18 to the 3/2 plus c. So you got to do that last little step, and then you'll be good. Yay. How could you check it if you wanted to? Elias, what could I do if I was looking at that going, yeah, I don't know, it doesn't look right? Yeah, the derivative. So if you do the derivative, the 3/2 times the 2/9, the 2's will cancel, 3 will cancel with one of the 3's here. Subtract 1 from the exponent, that'll give me something to the 1/2 power, times the derivative inside is going to be a 3x squared, and that 3x squared, the 3 will cancel with the remaining 3 here. C's gone, I'll end up with exactly what I have here. So it does check. Takes a little bit, but it does check. It's kind of nice. So how do they figure out, well, what should I let u equal? The trick in deciding u comes with one thing. You ready for that one thing? It's practice. Sorry. There's not any nice general, I mean, boy, some crestfallen faces that I'm seeing here. Like, really? I wanted you to give me this killer insight from decades of teaching this. No, I'm sorry. It's just practice. Now, I will give you a couple guidelines a little bit. One thing you're looking for is part of the problem to be the derivative of another part. So, in particular, when you're dealing with polynomials, when you differentiate an x cubed, you're going to have something that has an x squared, right? The degree always decreases. Or if you have a tangent in one part, secant squared might be in another part. So again, that would be a good substitution pair for a u and a du kind of term. But in general, the derivative of your u has to be in here at least up to a constant. If that constant's not there, we can work around that constant, but your derivative mostly has to be there. So let's do another one. I'm going to help you out with this one. It's not quite as clear what to let u equal because you're looking at this, well, in the last one, yeah, I can see that derivative of an x cubed is going to have an x squared. But let's take a look at this part right here. A lot of times it's nice to get rid of a binomial term and just collapse it down into one little piece. So let's let u equal 1 minus 2x. And then I'll differentiate both sides. Du by dx. What's du by dx going to equal? Negative 2. Yeah. Or, and Eura's going ahead of me a little bit, but that's great. Du equals negative 2 dx. That's wonderful. Except when I look up here, all I've got in my integrand is a dx. I don't have the negative 2. So what can I do about that negative 2? Well, let's move it to the other side. Now, other than dividing by negative 2, what can I do to move it to the other side? Yeah, multiply by the reciprocal, which is going to be a negative 1/2. So let's put that negative 1/2 out in front. You get negative 1/2 du equals dx. Perfect. Now I've got a nice substitution. I know what my dx term is. I can replace it with this term right there. The rest of this is going to be u to the 8th power. That's great. I think we can integrate that without too much sweat. So let's take a look. Integral of u to the 8th times minus 1/2 du. That constant you might find annoying, so let's move it out front. So it's going to be negative 1/2 the integral of u to the 8th du. And that's perfect. Notice that everything is in terms of u. It's either in terms of u or terms of x. You can't mix them up. So if somehow or another you substitute and you've got some x's left over, there's something wrong. Let's keep going. This part, well, that's not too bad. We can find the antiderivative of this. Now don't try and do everything all at once. Let's just leave the minus 1/2 out in front. What's the antiderivative of u to the 8th?
8u to the 7th.
8 to u to the 9th.
Oh, that's...
Oh, yeah, that's the derivative.
Yeah, 8 to the 9th over 9.
All right, so u to the 9th over 9. Help me out a little bit more.
Over 9.
Over 9 plus c. There you go. Plus c, our constant of integration. And now let's clean it up in two ways. First of all, let's multiply the fractions together. I get negative 1 over 18. And I also got to go back and replace the u. So it's going to be 1 minus 2x to the 9th plus a constant. And there you go. Nice. There's our antiderivative of that second one. How are we looking here? Doing all right on that one? You ready to try one? That's a yes. All right, good deal. Thank you. So, integral of cosine of 3x dx. Now this is really close to something that we can find the antiderivative of. In fact, if this was a little bit different, you could do it directly. What would you need to change? What would this need to be if you were just going to do it directly? Not cosine of 3x, but cosine of x. So that's kind of suggesting the substitution that they actually give you in this problem, and that is u is going to equal 3x. So there's your u. See what you can do. I didn't mean to make a rhyme out of that, but that's kind of cool. All right, give that one a shot. Help each other out. I'll try and help you out as well. each other out. I can't always get around to everybody. All right, so first things first, we'll differentiate both sides. We get du by dx equals 3, or du equals 3 dx. And then you can look back and see what's in your integrand. You've got a dx term there, you got a dx term there. So I'll push that 3 to the other side in the form of multiplying by the reciprocal. Now we're in good shape. There's my dx. If I replace dx, I can replace it with 1/3 of du. So we're all set now. That's going to be the integral of cosine of u times 1/3 du. The 1/3 I can bring out in front. That's just a nice what is called linearity property of an integral. What's the antiderivative of cosine? What do I differentiate to get a cosine? Sine. It'd be the sine of u plus a constant. And so, let's see. That's going to be 1/3 of, I can't leave it as a u. What do I got to replace it with? 3x. U is equal to x, 3x, so put in the 3x there, plus a constant. Nice. Nice. Abby, how could I check that if I wanted to? If I was like, you know, I'm not really so sure. I want to check my answer here. What could I do? Yeah, differentiate this. Derivative of sine, that's the outside function. Derivative of sine is cosine of the inside, so that's good. Times the derivative of the inside. What's the derivative of the inside? Derivative of the inside is 3. 3 times 1/3 is going to cancel, leaving me with cosine of 3x. Derivative of constant is 0. So, looking good. Looking good. Let's do a couple more here. Actually, a bunch more. And then we're going to get to the definite integrals as well. Anything else on this last one? All right. So one of the things you're going to find that you'll end up doing a lot of in Calc 2 is differentiating, or excuse me, integrating things that have trig functions multiplied together, various powers. Now, there's a couple possible substitutions here. And let me show you one that doesn't work. If I looked at this and said, well, you know, the derivative of cosine is sine, then yeah, hey, that's good. I see a sine there. Don't copy this down. If I did say u equals cosine of theta, du equals minus sine of theta, or du equals minus sine of theta d theta. But when I try and do my substitution, well, sine squared, that's sine of theta times cosine of theta d theta. If I kind of stretch it all out, I got sine of theta d theta. That's fine. I can mess with the negative part later. And I've got u equals cosine of theta. But I'm kind of running out of stuff, right? I haven't figured out how to get rid of that sine of theta term. And so as a u substitution, this isn't going to work. And you're going to run into that sometimes. You're going to choose the wrong thing for u. And that's okay. You're just going to go back and try it again. Now sometimes your choice of u might be a little bit more obvious. Like in this case, When you differentiate a squared term, you're going to get a term in x. So that U substitution might be a little bit more obvious. Here, our choice is going to be u equals sine of theta. And let's take a look at the difference that that makes for us when we differentiate this, when we try and set up our integral. If u equals sine of theta, let's just skip down to the du equals cosine of theta d theta. All right, that's great, because that's exactly what I've got here, cosine of theta d theta. So I can make a nice one-for-one U substitution. What's the difference between this and the last one? Here, sine of theta is u, so this is really going to become the integral of u squared du. Wow. Hey, wait a minute. Where's the button?
That was easy.
Yeah. That one worked out pretty nice, right? So what's the antiderivative of that one? Come on, I should hear a chorus of you guys. Antiderivative of u squared is going to be u to the third over 3. That was kind of weak there. Should we try that one again? All right. U to the third plus a constant. But please don't leave it like this. Your original problem was in terms of theta, so you got to go back and rewrite it. I'm going to write that 1/3 out in front. 1/3 sine of theta cubed plus a constant. Now, there's another way you can write that that's a little bit more convenient. It's a little notational convenience we allow ourselves. We'll just write it as sine cubed of theta plus a constant. They both mean the same thing. I'm happy to get it either way from you on an exam. Either way, my inner child will be doing somersaults. So, question on that one? We looking okay on these? Look, I was kind of joking a little bit earlier, but really, I mean, what makes you good at these things is practice. It's just like anything. If you want to get good at something, you're going to practice it, and U substitutions is no different. This one, you're going to let u equal 1 minus x squared, and that one's going to be a DIY thing. What's DIY? Do it yourself, yeah. All right, we're not going to do that one in class, sorry. But, you know, if you need some practice, etc., then try it with that substitution. We're going to focus on this last one, so I'll call that one example F. The integral of dx is 5x plus 8. Now the thing that you got to keep in mind with these integrals is that if you're going to have success with them, you have to make them look like something you can integrate. And I'll help you out this much to start with. I can write that as 1 over 5x plus 8, and then I'll just push the dx off over here. I've got to find something that when I find its antiderivative, I'm looking at something that differentiates to get this. Now that's kind of close to something we know how to integrate. What does it just feel kind of close to? Yeah, it looks like a natural log kind of thing. It looks like a 1 over x. But I don't have 1 over x, do I? I've got 1 over 5x plus 8. Is that suggesting a substitution at all? What substitutions does it suggest? U equals 5x plus 8. Exactly what I have right there. So why don't you run through that U substitution and see if you can make it work. While you do that, I'm going to open up a couple links here. got your U is here. You solve for dx here. So rewrite the integral as 1 over u and then times that. And then I'll put everything in terms of u. Oh, that's going to be off up there. And the antiderivative of that. Plus, yeah, you want to get rid of the du, put a plus a constant instead. Use du here. Du comes from because of dx. So I guess so put du there and then find the antiderivative. Okay. All right. So let's work this out. Now, a lot of you have already gotten comfortable with this. Instead of doing du by dx equals 5, you just jump to du equals 5 dx. And that's fine if you're comfortable kind of skipping that in-between step. That's no problem. We want to solve for dx because we have the dx in the integrand. So that's going to be 1/5 of du equals dx. Now I can make a nice direct u substitution. That's going to be 1 over u times 1/5 du. 1/5, maybe it's a distraction, maybe it's helpful to bust it out in front. 1/5 times the integral of 1 over u du, which is the same thing as du over u, if you wanted to think of it that way. 1/5, let's see, it's a really ugly looking 1/5. So 1/5 ln of u. Technically, it has an absolute value there. Ln of the absolute value of u plus a constant, or 1/5 ln of 5x plus 8 plus your constant. Yay! I forget why. Yeah. In part because you have to make sure that the absolute value is positive, or that you take the log of something positive. So the absolute value does that for us. You also can't take the log of 0, so it's not completely right, or it's not completely foolproof, but yeah, technically I think you do need the absolute value there. Okay, looking good. Let's move on to work with definite integrals. And so there's a couple different ways you can handle definite integrals. I'm just going to give you the way that I prefer, the way I think is the easiest and the most efficient. So maybe put a little big note in your notes that you're taking, definite integrals. Because there's an extra step here that we're going to have to do when working with these things. So that extra step is going to look like this. Integral from 0 to 1 of the cube root of 1 plus 7x dx. A lot of you might start out by saying, oh, well, I got this. That's just the integral from 0 to 1 of 1 plus 7x to the 1/3 power dx, and that's fine. But you still can't directly find the antiderivative. So at least in your mind, if not on your paper, you're going to have to do some kind of a u substitution. Does anything suggest itself in this problem? James?
1 plus 7x.
Yeah, let's do the 1 plus 7x. So I'm going to let u equal 1 plus 7x, and that's going to mean du is going to equal 7 dx. So you get du by dx equals 7, multiply both sides by dx and get this. And if you're all happy, you're like, okay, well, let's see, that's going to be 1/7 du equals dx. That's great. You can change both of those things, but there's one more thing we have to change. These limits of integration are for the variable x. They're not for the variable u. So I'm going to rewrite this as u of x equals 1 plus 7x. And I got to feed in the values of x equals 0 and the values of x equal 1 into this to get my new limits of integration. U of 0, u of 1, u of 0, u of 1. Plugging in a 0 there, I'm just going to get a 1. If I plug in a 1 here, what will I get? 8. Those are my new limits of integration. Now I can go ahead and do this one. That's going to be the integral from 1 to 8 of u to the 1/3 times 1/7 du. Now there's another nice advantage of doing it this way. Whereas with our indefinite integrals, eventually you had to go back to units of x or whatever your original variable was. Here, we're just going to finish the problem in u. We've changed our units. All we have to do is just finish this calculation. We don't have to go back to our old units. So let's just do that. That's going to be 1/7 times the integral from 1 to 8 of u to the 1/3 du, or 1/7. That's going to be our constant out in front. 1 to 8. Now remember, you've already found the antiderivative. I don't need to keep that as an integral symbol. In fact, it's wrong to do that. I want a straight line here. That's going to be u to the 4/3 power divided by 4/3, which is going to be multiplying by the reciprocal, 3/4 u to the 4/3. Let's bring that out in front. 3/28. The integral from 1 to 8 of u to the 4/3. And finally, that's going to be 3/28. 8 to the 4/3 minus 1 to any power is 1, like that. 8 to the 4/3 works out nice and evenly. That's going to be 16. 16 minus 1 is going to be 15, times 3 is going to be 45. Should end up with 45/28. That will be my final answer.
So that's when I did it, I got 48/28. I might have done.
Maybe you didn't subtract the 1 here. I'm not sure. I'll tell you what. Let's just check it numerically. All right. So let me clear this stuff out. And math 9. Let's see. 0 to 1 of. Now you're going to need to be a little bit careful here. You can type in cube root directly if you want to go to the math menu. I'm just going to type it in as something to the 1/3 power. 1 plus 7x raised to the 1/3 power. 1 divided by 3 with respect to x. And let's hit the math key. 45/28. So looking pretty good. All right. Comments or questions on this one? The one thing I want to emphasize is that once you do your U-substitution, once you change your units and your limits of integration, you don't have to go back. And that's what's really nice about this one. If you do want to change your units, or if you just kind of want to use this to get a U-substitution and then finish the problem in X, you can do that. I wouldn't recommend this, but here's what it would look like. So, alternatively, and I'm not even sure I want you to copy this. I don't like it this way. I think in a little spirit of rebellion, my daughter does it this way. I think just to make me mad, something, I'm not sure. Any case, she does it differently, and it works. It's fine. If you didn't want to change your units of integration, then you wouldn't have to, excuse me, your limits of integration, you wouldn't have to go back and find these numbers, but here's what it would look like. We would rewrite this as the integral of u to the 1/3 times 1/7 du, but it's wrong to leave this as 0 and 1. I'd be uncomfortable to the point that I have to think about taking off a point because your limits are different. So what you could do is just write down, well, I'll just put down alpha and beta. Just a couple other numbers or something to take the place of that. Then we'll find our antiderivative. That's going to be 3/4 of u to the 4/3, and then I'll have the 1/7 out in front between alpha and beta. Then I'll rewrite that as 3/28 times the integral of u to the 4/3 between alpha and beta, 3/28. Now I'm going to go back and substitute in for my original variable. So I can put in the limits 0 to 1, and I'll put in 1 plus 7x raised to the 4/3, and then it finishes up kind of like you would expect, 3/28. If I put in a 1 here, I'll get 8 to the 4/3 minus 1 to the, or excuse me, 0 plus 1 is going to be 1 to the 4/3, and that'll give me my 45/28 as I got before. I just don't like it that way. It's up to you. If you like it that way, that's fine. I'm not going to micromanage you, but I'm going to do it this way. Any votes? First way or second way? Which way you're most comfortable with? First way? All right. Second way? Okay. Second way? All right. Got a rebel. Always got a rebel. All right, that's fine. Let's do a couple more here. This next one. This one's kind of cool. It has a couple things in it I want you to see as we do this. So let's look at example H, and it's going to require us to also think about what are called even and odd properties of an integral. So I've got the integral from -2 to 2 of x plus 6 times the square root of 4 minus x squared dx. Now this one has a couple tricks into it. Eventually we are going to do a little U-substitution for part of this, etc. We'll see about the other part. So one thing I want you to notice is I've got what's called a symmetric interval. And that's going to be kind of interesting. So we'll keep that in the back of our mind as we're looking through this. But I'm going to distribute this square root term to both of these terms here. In fact, I'm going to break this integral up into two integrals. So I'm going to break it up into -2 to 2 of x times the square root of 4 minus x squared dx plus the integral from -2 to 2 of 6 times the square root of 4 minus x squared dx. So again, just using the linearity properties of the integral to break that up. Let's think about both of these, and let's see if we can save ourselves a little bit of work here. Now, in particular, I could take and factor out the 6 here, and I have 6 times the integral from -2 to 2 of the square root of 4 minus x squared dx. Let's not forget what that means in terms of its geometry. What does that actually represent? right here. What does that mean? Don't worry about the 6. What are we finding here? Well, it's convenient that we have a backside to our handout. Because the backside gives us this graph. So let's interpret this interval in terms of the graph. What am I trying to find here? Area underneath the curve. Can we be more specific about the curve? From -2 to 2, good. Can anyone tell me anything about the area of that curve? The area underneath this curve that I'm shading in orange. Wow. I actually managed to stay inside lines. That's unusual for me here. So, all right. But do I need to use calculus to find that area? What's the shape here? A semicircle. So the area is going to be 1/2 times pi times r squared. What's the radius in this case? So 2 squared. And, well, 2 squared is 4 times 1/2 is going to give me 2. So 2 pi. Wow. Now keep in mind I got the 6 out in front still. And let's see, work on page 20. Man, we're 20 pages into these notes here today. That's about where we usually get, in case you're curious. So let's work on that last one. We've got the integral from -2 to 2 of x times the square root of 4 minus x squared dx. Man, that looks like a lot of fun. I'm going to sit back and relax while you work on that. Oh, all right. Well, maybe not. But maybe you can help me. What would you do for something like this? Nice. Not sure if you're as quick as that, but let me help you out here. If you take a look at this, when you differentiate an x squared term, you get a term in x. So that's kind of hinting and nudging you at making a particular type of u substitution. I'm going to call it u of x because I want to change my limits of integration. U of x is going to be 4 minus x squared. Du by dx would be minus 2x, or simply du would equal negative 2x dx. Let's take a look at what I have in the integrand. I've got an x and a dx. I've got an x and a dx there. Hannah, suggestions. What could I do here? I want to eventually replace that, but it's not an even swap because I don't have a -2 in my integrand.
Oh, you're just going to move the 2 then you're doing the du side?
Yeah, we want to move the -2 to the du side, so when it moves to the du side, what's that going to be?
-2 du.
Well, you got to multiply both sides by the reciprocal, so that'd be -1/2. Great. There's something else I got to do here. Does anyone know what it is? What did I do in the first problem where I had to do a u substitution like this? I got to find my new limits. Now our new limits are going to give me something kind of interesting. There's going to be an interesting result when I do my new limits. So let's take a look here. I want to find u of 2 and u of -2. 2 and -2. Help me out. What am I going to get when I figure out my new limits? Four minus 4, well, wait while I get out my graphing calculator. And 4 minus 4 again, right? 0. Well, that's looking weird. Let's put everything together and put it back in our integrand. I'm going to replace this with a u, and the square root I'm going to replace with something to the 1/2 power. So I'm going to go from 0 to 0 of u to the 1/2 power. Instead of x dx, I can write negative 1/2 du. That negative 1/2 can come out in front. Negative 1/2, the integral from 0 to 0 of u to the 3/2 du. Well, not u to 3/2, I haven't found the antiderivative yet. U to the 1/2 du. The antiderivative of that is going to be to the 3/2 times the 2/3. So I'll end up with negative 1/2 times 2/3. 0 to 0 of u to the 3/2. But about 2 minutes ago, Elias was looking like, well, why are we even bothering to do this? I mean, this does cancel to negative 1/3. But what's going to happen when I substitute in these values? 3/2 to the 0 minus, or 0 to the 3/2. What do I end up with? 0. Well, that feels disquieting. It feels like, ooh, that doesn't feel right. And we did all this work for nothing? Let's take a look at things graphically and understand what's going on. This is the graph of that function. So you've got an area here. I want to find the area of that function between the curve and the x-axis. And then another one down here. Can anyone explain in terms of geometry why I ended up with a 0?
They cancel them out.
Yeah, they cancel each other out. This one and this one are the exact same thing, except that this one's below the x-axis, this one's above the x-axis. So when you integrate there, you get a big goose egg. That's because this is an odd function. If you have an odd function over a symmetric interval, that's going to happen. So if you got an odd function over a symmetric interval, it's probably a good thing to notice it. So in general, and let's see here, do I have, oh, let's see. In general, let's write down ourselves a little rule. This is the odd function rule. So f of x is an odd function. Then the integral from negative a to a of f of x dx is 0. Boy, that's a nice time saver if you can spot that on an exam. I mean, it doesn't, doesn't kill you if you miss it. You'll eventually get 0, and then you'll be like, oh, man, I could have saved myself 5-10 minutes worth of work. All right? You'll end up with 0 either way, just like we did right here. So it's helpful to be able to spot odd functions. Odd functions are functions that are symmetric with respect to the origin. And I'll show that in just a minute. James?
On the exam, if there's one of those problems, do you want us to write the whole workout?
No, great question. On the exam, if you spot this, just write odd function rule and then write a 0. No, I don't want to see that work. I want to reward you for being clever enough to spot that. So yeah, just write a 0 there and write odd function rule. If you just wrote a 0, I'd be a little uncomfortable because you could get that answer with just fn int. And I don't want to just give you credit for knowing how to use your calculator. I want you to understand the calculus. So thanks for that question. Let me see if I think I got a link here that allows us to practice those things. So there's another property that you can look at in terms of functions and integration. If you have an even function, then with your even functions are symmetric with respect to the x-axis. So what you can do is, if you have an even function, let me see if I can't find a spot in my sheet here for an even function. See, odd function rule. Now, let me just write it down here at the bottom. Even function rule. If f of x is an even function, then if you're integrating again over a symmetric interval, negative a to a of f of x dx, well, maybe you can tell us a shortcut. It's not going to turn into 0. So this is an example of an even function, x squared minus cosine of x. What do you notice about this function that is kind of noteworthy? Interesting. Does it look kind of similar from the left half to the right half? It's symmetric with respect to the y-axis, right? So finding the area between this curve and the x-axis is really adding up this region and this region and this region and this region. But what can you say about the green area compared to the red area? They're the same, right? And the blue area and the orange area, again, the same. So you're really finding these areas twice. So what you could do is just find the areas once and then double it. In other words, twice the integral from 0 to a of f of x dx. It's not as huge of a savings as the odd function rule, but it is a nice savings. So it's worth doing if you see it. A lot of times it's easier to plug in a 0 than it is to plug in some number. So it can help you simplify things there. We're going to finish this up by looking at some of these things and trying to decide if they're even, odd, or neither. You can practice this if you're watching this later with the QR code here and take a look at these things. So you can practice them yourself. Let's just buzz through these now. That should take us right to the end. So let me shut off those and turn on this one. Let me try and coax you a little bit into understanding what an odd function is. An odd function has what's called origin symmetry. And if you draw the line y equals mx, then anywhere that this line moves, you're going to find symmetric points on the graph, symmetric points on opposite sides of the origin. If you take a look at these points, they're mirror images of each other, just opposite signs. No matter where I'm at on this curve, it always has that property. So that's what an odd function looks like. It's not something that has the nice striking visual symmetry that an even function does. So let's shut these off and let you decide. Yeah, I should probably zoom out a little bit. What do you think? Even, odd, or neither? There's an odd function. Good. So odd function there. Let's take a look at the next one. Let's see. Let me try and, I guess it doesn't really exactly matter if I have it squared up. Even, odd, or neither? Yeah, that's a neither. How about the natural log function? Even, odd, or neither? Is that even? Is it a mirror image on both sides of the y-axis? Here's what it would look like if I had a mirror image on the other side of the axis. That would be something like this would be an even function, but with just one of those branches, it's a neither. How about 5 times the sine of x? Yeah, sine is an odd function. You'll understand a little bit more about that in Calc 2 when you look at the series for a function like sine. So this is going to be an odd function. One nice thing about Desmos is that it can graph the secant function In fact, it can graph the secant squared function, which is going to look like this. Even, odd, or neither? Even. It's symmetric with respect to the x-axis. So we got a nice even function there. Four x minus x cubed, next on tap. Let's do that one. There's your odd function. So if you see stuff like this, you know, your odd functions over symmetric interval, please take advantage of it. I'm putting it there to be kind to you. And then, last but not least, the big W, even. So take advantage of those symmetries when you see them. And go ahead, see if you can't figure out the password for the free Wi-Fi. It's actually pretty clever. It's actually a clever problem. Good luck, and see